6. Here's our last example of graphing a rational function. Okay, so again, our 7 steps. Step 1, factor completely. It does not factor. It's just linear in both the numerator and the denominator. Step 2, find the domain. So we take the denominator, set it equal to 0, and that's what the denominator or the x value of the domain cannot be. So x cannot equal -2, because if we plugged in a -2, we would be dividing by 0. Okay, step 3, we're going to do our x-intercepts. So we just take our x plus 1 and set it equal to 0. That's just our numerator. So x equals -1. So that's our x-intercept at -1, 0. I'm going to sketch that in my graph. And then for the y-intercept, we're going to plug a 0 in for x. So 0 plus 1 over 0 plus 2 is 1/2. So that puts a y-intercept at 0, 1/2. So about right here. Okay, next, item 4 is our vertical asymptote. First, we make sure we reduce, so I'm just going to say it doesn't reduce. Kind of mushed all that together. Anyway, and our vertical asymptote is going to be at x equals -2, because that's the value that would make this 0. That's where the domain doesn't exist. That's where the graph cannot cross, yada yada, all the things. So we are going to go ahead and put a line, dotted line for our asymptote at x equals -2. The x equals part is important so that you know it's vertical and not horizontal. All right, next we are going to do step 5, which is horizontal asymptote. So notice how the degree of the numerator is 1, and then the degree of the denominator is also 1. So when the degrees are equal, that means our horizontal asymptote is going to be at y equals our leading coefficients. So 1 divided by 1, which is 1. Let's go ahead and throw in that horizontal asymptote right here. Oh, I put it in the wrong place. I put it at 0, when in fact it goes at 1, because those were our leading coefficients, right? Okay, step 6. Remember, I changed my color to orange on this one. I don't have to keep the same colors, but it was kind of fun. So 6 is just to plot in some other points. Right now we know quite a bit over here. In fact, I'm guessing we could pretty clearly put our branch of our graph here. We could plug in something like -1.5 to see if there's going to be a point right there or not, but I bet there is. Let's go ahead and do that. So -1.5. That would be in the numerator. -1.5 plus 1 would be -0.5. And then in the denominator, -1.5 plus 2 would be +0.5. And so that gives us a -0.5 divided by a +0.5, which is -1. So if we go left to -1.5, we go down to 1. That definitely fits the symmetry of that branch of our graph. Okay, let's try another point, maybe over here at -3. So -3 plus 1 is -2, and -3 plus 2 is -1. That gives us a point at +2. So left, 3 up 2. There's the first point of this other branch of our graph. We could do some other points on each side just to make sure, but this isn't going to cross the asymptotes. So I'm pretty confident that we know where this branch is just based on this one point. All right, let's put it all together. Step 7, here's our graph. Let's see if I can sketch this better than I did the last one. Oh, that was quite a bit better. And maybe I'll look at on this one too. Ooh, I must be getting better with practice. So there is our reciprocal graph. But how do you, what's different about this one than in our previous one? Do you notice? Like, example 6, we were in the top right and the lower left. Example 7, we're in the top left and lower right. Does that mean that there would be some sort of like reflection going on here. There should be a negative. Well, this is not in transformation form. We've got this extra 1 written on the top. Now, if you really want to see this other way of dealing with this by graphing with transformations, this could be fun. The first thing we have to do in order to graph this with a transformation is to make sure that the degree of the numerator is smaller than the degree of the denominator. We can't have an x in both the numerator and the denominator because, you know, our reciprocal function is just 1 over x. Correct. So the first thing we actually need to do is divide the denominator into the numerator. Sounds a little tricky. We could do it with synthetic division if you want to, but I'm just going to go for it. So x plus 2 divides into x plus 1 once. 1 times x plus 2 is x plus 2. Draw the line, change the sign. That's going to give us a negative 1 here. And x plus 2 obviously doesn't divide into negative 1. So what's happened here is when we divided x plus 1 or x plus 2 into x plus 1, we got a quotient of 1. So 1, we're going to say h of x equals 1, but then we have a remainder of negative 1. So the remainder is negative 1, and then that remainder of negative 1 is out of our divisor of x plus 2. This is similar to how you would do a mixed number, like if you had something like 7/5. 5 divides into 7 once with 2 left over, so that would be 1 and 2/5. So same idea here. Now maybe we can actually see the transformation and that it matches our graph. I'm going to switch this in the order we're more used to seeing a problem like this in. Now notice we have this negative because our remainder was a negative number. That negative gives us our reflection. Thus our graph is in the upper left and lower right instead of the other way around. The x plus 2 gives us our shift to the left 2. That's why our vertical asymptote is at negative 2. And our plus 1 gives us our shift of down. I wasn't going to write the word shift, and then I did it anyway. Our shift up 1, our k value, and that's why our horizontal asymptote is up 1. So this isn't something you have to do. You don't have to do this on every problem where you graph it both this way and with transformations. I just really wanted you to see that connection between what we learned in Chapter 1 about graphing this as a transformation of a reciprocal function and what we just learned in Chapter 3 with just all of these characteristics and using them to graph our rational function.